begin. Okay. Oh, by the way, did you figure this question out? And Hania, your answer was right. That was correct. Yes, Ariz.
Yeah, I did this question.
You
I just
did?
didn't
Okay.
send it to
Huh.
you.
Okay. Okay. You can
Should I
send
send
it
it to
later.
you now?
If
Or
you have your phone right now, you can send it. I'll check it out.
okay.
If not, then you can send it later. Are you sending it?
Yeah, I was sending it. However, my graphs are not like
Oh, that's
it's
okay. That's
not
okay.
that
It's rough. That's
accurate.
fine.
Okay. I send the first photo to you. I'm sending the second one.
Okay. Uh, okay. Yes, that's right. Okay. And force is roughly over here. Okay, that's also right. Yep, that's right. Okay. The acceleration would have a similar curve, sorry, a similar rectangle, but for different values of A. That's right. Okay. You just have to like convert the force into acceleration. That's right. So it would look something like this and
Yeah,
like this, and then the
I did
acceleration would
just that
also be
actually.
very similar to the force graph. Why? Because acceleration is just force divided by the mass. It's just force divided by the mass. So that's how you would like the graph for force and acceleration, by the way, is always of the same shape, not the same values, but the same shape. Why? Because acceleration is just force divided by the mass. Okay, so the shape would be the same. The it's just the values that would be different. Okay, sounds good. This would also look like this. Okay. Yeah, Hania, did you watch the lecture from Wednesday? Sorry, not Hania. Sorry, Kaima. Kaima, did you
Yeah,
watch the lecture recording?
yeah, I watched it.
Okay. Did you get it? Any questions up till now?
Yeah, I tried the last question that you.
Okay. Okay. Any other questions? Something you did not get? We just did questions, all of these.
No, I got them.
Okay. Let's move on. So now moving on to, we're done with Newton's second law. Second law was what? Resultant forces change, rate of change of momentum. How quickly momentum changes is equals to resultant force. Okay. And we even like drew the graph of it. And we know that the slope of a momentum time graph is what? The slope of a momentum time graph is resultant force. And the area under the graph of a force time graph is what? That's just change in momentum. Okay. Make sure you keep that in mind. By the way, delta P over delta T is equals to resultant force. This is average. And if you want to like talk in terms of if you want to talk in terms of mathematics, if you want to be even more precise, that you could say that dP over dt is resultant force, which means the derivative of momentum with respect to time is resultant force. Okay, so that's an alternative way of thinking. That's what we do in mathematics, which is more precise. Okay, but that's not really required for A-level physics. Okay, now moving on to Newton's third law. Yes, Hania, do you know what Newton's third law is? Pretty easy. It's pretty common. It's the one that everyone knows.
For every reaction, there's an opposite or equal reaction.
For every action force, there is an equal and opposite reaction force. Now, although everyone remembers this definition, everyone has learned this law, but can you give me an example? What do you think? Ariz, what do you think? What could be an example for this? Where do you even see this Newton's third law? Does it only apply in like very specific cases?
Is it like when you push something heavy? I mean, like you
Hmm.
even get pushed back,
Mm, okay. You get pushed back. Okay, that's
or
also
like
true.
when you're pushing something, the same force is being applied onto your hand. Like
Exactly, exactly. For example, if you try to push a wall, you apply force on the wall, but why does your hand hurt? That's because the wall is applying the force on you, right? There's like
yeah,
tons and tons of examples. I'm going to grill all of those examples with you, and you will see that Newton's third law is much more visual and much more common than we think. We just think like, we just think of something pushing back on us, but absolutely everything that you do is dependent upon Newton's third law. For example, for example, uh, for example, we know that any free falling object is going to be pushed down with an acceleration of g, right? If g is 9.81, right? That's the value of free fall of acceleration, right? And we also know that there's going to be a 9.1 Newton force for every kg. So that means Earth is going to pull down 1 kilogram of object with a force of 9.81, right? That's its weight is equals to mg. 1 kg multiplied by 9.81, that means the weight of a 1 kg object is just going to be 9.81. Okay. Now, if Earth is pulling you down with a force of 9.81, okay, then you should also accelerate with this value. Okay. So Newton's third law says if there is a force on you, right? In this case, the force is you free falling. Okay. If there's a force on you, you should accelerate. You should accelerate. Right. So that means if, for example, if the cat has a force W on it, okay, then the cat should be accelerating downwards, right? The cat should be accelerating downwards with a value of G, right? That's what we learned. If anything is falling, it's going to have a force which is equals to the weight on acting on it, right? And it's going to accelerate downwards with the value of G, okay? But then the question is, if there is always a force and of an acceleration due to gravity on everyone all the time, why doesn't the cat fall into the earth? What do you think? Because earth is constantly pulling the cat down. Why doesn't the cat just fall into the earth? What do you think? Any idea? Yes. Yes, Kaima, what do you think? Why doesn't the cat fall into the earth? Seems like a pretty dumb question, but it's an excellent question. If earth pulls everything down with the constant force, with the constant acceleration g, why doesn't the cat fall into the earth? Yes, Aris, what do you think?
I'm not sure actually.
Okay. For example, obviously right now, the earth is applying a force on you, right? Which is equal to the weight. You can even check that on the weight machine. It's going to give you your mass though. But there is a force on you, right? There is a force on you, and if the force acting on you is the weight, okay, then your acceleration downward should be g, right? We know that if an object has a certain weight or w, then that ball or that object should have an acceleration downward called g, okay? But why doesn't the ball fall into the ground? Why don't you fall into the ground? Now, this is what? This is the force of you, of the cat on the floor, right? Now, why doesn't the cat fall into the floor? The only reason could be that there must be an equal and opposite force due to the floor, right? This is the floor's reaction force. This is what we call the normal force. This is what we call the normal reaction force. You are standing right now, or you are sitting in your seat right now because of Newton's third law, right? Earth is pulling you downwards with the force of W, right? And why don't you fall down into the floor? Why don't you accelerate downwards? That can only imply that there must be an equal and opposite force from either the seat or your feet or your floor or your whatever you're standing and sitting on, right? It will apply an equal opposite force on you to stop you from accelerating, right? Now, what is the resultant force in this case? If weight is equal to normal force, I'll write this as N, okay? Then doesn't that mean that resultant force is zero? And doesn't that mean acceleration is zero, right? Because F is just equal to ma. If this is zero, this is also zero. If there's no force, there should be no acceleration. And that makes sense. That's exactly why you don't fall into the ground. That's it. Because the ground is pulling or is pushing back on you. The ground pushes you back. Pushes you back. That's why. That's why you don't move. That's why the cat doesn't fall into the earth, right? But imagine if there was no floor. If I remove the floor, what would happen? There would be no reaction force. That means the cat would then continue falling with an acceleration of g, right? So that's why you will see that if you have a force on the floor, okay, then the floor will apply an equal and opposite force on you, and that's exactly why you don't fall into the earth, right? For example, if you have your hand on the table, okay, now you are applying a force on the table. Why doesn't your hand fall into the table? Why doesn't it like phase through? Because the table is applying an equal and opposite force on your hand, and that's why your hand is not moving, right? Because if there was no hand, sorry, if there was no table, then you applying the force would just push through your hand, and your hand would just go down. Okay, so all of these examples are Newton's third law. I'm going to give you much more examples, but first let me show you a really good video. Check this out. This is Newton's third law demonstrated in space. It's such an excellent video. Check this out. Here it is. Can you hear the audio? Can you hear the audio?
Welcome to
Yes,
Yeah.
Aris. Yes, okay.
the International Space Station. I'm NASA astronaut Mark Vande Hei. Today, we're going to talk about Newton's third law. How do you think it will hold up in microgravity?
For every action, there is an equal and opposite reaction. This means that in every interaction between two objects, there are a pair of opposite forces acting on each object at the same time. A force pair. You can see that there are many examples on Earth. In space, thrusters expel one way and the vehicle is steered in the opposite way.
Hello again. More basketball stunts that I can't do on the ground, at least not while getting this much hang time. All right, back to serious business. We've got a basketball right here. It's going to be object 1. I'm the second object. If object 2, myself, applies a force to object 1, then that same force will be applied according to Newton's third law by object 1 onto object 2. However, there's a big disparity in the mass. Object 1 is a very light mass object. Object 2, myself, is a larger mass object. So I'm going to try to make myself about the same shape as this ball. See how that works for us. And I'm going to apply that force. You saw that force applied to the ball made it accelerate quite a bit. It really didn't accelerate me much at all. Newton's third law again, but this time we're going to use two similarly massed objects. Joe and I have about the same mass. So Joe, get into a ball. I'll do the same. I'm going to face you this way so that I don't throw you into something you can't see. Now I'm going to get into a ball behind Joe, and I'm going to apply a force to him. Notice that when I applied a force to Joe, it accelerated Joe away from me, but I got accelerated away from him as well, because the force applied to Joe ended up being the same force that was applied to me. Now you've seen Newton's third law in space. Now test it out on Earth. See you next time.
Check this one out as well. Such an interesting video. I think it was this one.
Today we're going to demonstrate Newton's third law of motion, which says
check
every
this out.
action has an equal and opposite reaction. It's the principle that sends rockets to the moon. If you want to try this at home, this is what you need. When I release my fingers, air pushes out of the balloon. That's our action. Our reaction is that the balloon moves with the same force in the opposite direction. If you want to learn more about Newton's third law of motion or ask me a question,
That's also an interesting demonstration. That's like very similar to how rocket propellers work, right? The force on the balloon, what happens is that out of the balloon, you've got air, right? So it's kind of like this air, I'll in fact write it out. The force on balloon due to air is equal and opposite to the force on air due to balloon. So what's happening is that the air is applying a force outwards, okay? The balloon is applying a force on the outside air, and the outside air is applying an equal and opposite force onto the balloon. That's why the balloon goes forward and the air behind it goes backwards. That's exactly how a rocket works. Not exactly, but very similar. Okay, so there are a few conditions for Newton's third law. Keep in mind that there must be two objects. Okay, you have to have two objects. They must be equal and opposite. They must be of the same type, and they must act on the same time. There's one other which is very, very important, which is often overlooked. The forces act the forces act on two separate objects. Okay, that doesn't mean that both equal and opposite forces are acting on the same object. Okay, so for example, you have this object and you have this object. Okay, let's say that they collide. Now, one second. For example, this is your hand. Okay, this is your hand and you're trying to push it. Okay, now since you are trying to push it, you are applying a force to the box, right? Now, the equal and opposite force would not be on the box, that would be on you, right? So this is the other force. So if you apply force on a box, okay, that force is going to be on the box, but the box is going to apply the force on you. Okay, so make sure you keep that in mind. So conditions: there must be two objects, force must be equal and opposite, force p must be of the same type, and they must act on the same time. And lastly, they must act on two separate objects. Very important. And you'll see that with a few examples. Don't worry. Okay. Question another one. Why does the Earth orbit the sun? We do know that, we're revolving around the sun, but why do we do that? Why does the Earth orbit the sun? And why isn't it that the sun orbits the Earth? What do you think, Hania?
It's because, like, maybe because of the size difference, like the Earth is smaller than the sun.
There is
And
that's definitely a fact.
so, like, because of like the gravitational pull or something to
It
like
does.
balance it
Definitely.
out.
Okay, definitely. In fact, did you know that there is Newton's fourth law as well? Did you know about that? This is
No,
called the law of gravitation. The
Why
law
don't
of
you teach us this?
gravitation. What are you saying?
Why don't they teach us this?
This is an extension of the second law. Extension of the third law, right? Now we know from Newton's third law. Oh, by the way, this is taught in A2. This is taught in detail in A2. Okay, but for A1, this is not really required. I'm going to teach you from the lens of Newton's third law. We know that Newton's third law just says that it's an equal and opposite force on absolutely everything. Okay, so if you apply a force on something, it's going to apply an equal and opposite force on you. Okay, now what's happening is, why does the Earth, I'm going to give you example, why does the Earth orbit the sun? Because we know that the sun is pulling the Earth with a force. Okay, keep that in mind. Sun is pulling the Earth with force F, or you could imagine gravitational force F. Gravitational force F. Okay. Now, does Newton's third law says? Newton's third law says that this is kind of like a special, you could say, variety or special extension of Newton's third law, that the Earth, what happens is, according to Newton's first law, if the sun is pulling the earth with gravitational force F, then the earth is also pulling the sun with an equal and opposite force. That's a fact. The earth, then, the earth is also pulling the sun with gravitational force F. There's an equal and opposite force on the sun due to the earth. Okay, that they're equal and opposite. So if this is, let's say, 200 newtons, this is also going to be 200 newtons in the opposite direction. Okay, so how strongly earth pulls the sun is going to be the same. Okay, now if there is a force, if there's an equal and opposite force, then why don't they just collide together? What do you think? If the same force is pulling the earth and the sun together, right, they seem to be attractive, right? If they seem to be attractive, why don't they just collide into each other? Or for example, another question would be, why don't they, or why does the earth move and not the sun? Also really interesting questions. And not the sun. It has to do, this question has to do with Newton's second law. Newton's second law. Why does that have to do with Newton's second law? Now, let's check this out. We know that both of these are attracted to each other with an equal and opposite force, right? The sun is pulling the earth with the force F, but so is the earth pulling the sun with the force F. They're both equal and opposite, okay? Now, why is it that the earth orbits the sun and not the sun that moves, okay? It's because of the difference in masses. Since since sun has a greater mass, that means it has a smaller acceleration. That's it. That's the answer. Because of Newton's second law. Since if the same force is applied to two objects, the one that will move is the one which has a smaller mass. And clearly the earth has a smaller mass, right? We can even check it. So let's calculate the acceleration of the earth. Acceleration of the earth is going to be what? Wait 1 second. What was the force? 1 second. The force of gravity between the sun and the earth is, it is 3.5 into 10 raised to power 22 newtons. Okay, so that means this is the force this is the force by how much the sun is pulling the earth, and it's also going to be the same force on the sun. Okay, now question, can we calculate the acceleration of the earth? Yes, we can. We can just use Newton's third law. Fr is equals to ma and a is equals to fr over m. What is the force that's being applied? 3.5 into 10 to the power 22. What is the mass of the earth? That's just what? That's 5.97 into 10 to the power 24. Let's calculate what the acceleration is. You can do it for me and tell me what the answer is. My calculator is, okay. Okay, acceleration of the earth is 5.86 into 10 to the power minus 3 meters per second square. Okay, now let's calculate the same thing for acceleration of the sun. We know that the force on them is the same, right? That's just 3.5 into 10 to the power 22. Both of them are being attracted by the same force. That's just Newton's third law's extension. Now, what is the mass of the sun? That's actually different, right? 2 into 10 to the power 30. Now, let's check what the acceleration of the sun comes out to. 2 into 10 to the power 30. That is 1.8 into 10 to the power minus 8 meters per second, right? Do you see how different they are? Do you see that this has a power of -8 and this has a power of -3? If you want to compare how strongly the Earth moves compared to the Sun, you can even take a ratio of that. 1 second. So if I were to divide them, 1 second, 5.86 into 10⁻³ divided by 1.8 into 10⁻⁸. Okay, so that means the acceleration of Earth is 32555 times more than Sun. And that's the answer. So clearly, because of the difference in masses, it's the reason why the Earth is going to move rather than the Sun. Even the Earth is trying to, sorry, even the Sun is trying to move, but the acceleration value is completely negligible. Whereas the acceleration value for Earth is actually very significant, and that's the entire reason why the Earth is going to orbit the Sun. Does that somewhat make sense? Yes, Anya.
Yeah, I got it.
Nice. Yes, Ariz, what about you? Did it make sense?
Yeah,
Are we?
it made some sense. Yeah.
Nice. Okay. Yes, Kaima, what do you think? Did it make sense? Why is it that the Earth is moving and not the Sun?
Yeah.
Yeah, okay.
That's what they
Nice.
said in the video as well, right?
Which one?
The video
I
that we
think.
watched, like if the masses are different, then
Ah,
like the
yes. Absolutely. Absolutely. There was a slightly different example, I think, not exactly this one, but yes, absolutely. Now, if, for example, if the same force is being applied to say the 1 second. Okay. Okay, sounds good. Okay, let's move on. Another question. Another question. Why is it that the moon does not fall into the earth? You see the same force of gravity on the moon which you see between the sun and the earth as well. So what is this force? This is the force. This is the force on moon due to the earth. Okay. Now, if the earth is pulling the moon, then we see that there would be an equal and opposite force on the earth due to moon. That's also a Newton's third law pair. Now again you would ask, why is it that the moon is orbiting the earth and not the earth orbiting the moon? Because of the difference in masses, right? If the same force is on both of them, the one that's going to move is the one which is with the lighter mass. Okay, and then if you want to answer the question, why doesn't the moon fall into the earth, right, if they're both attracted? Because the answer is that they're falling sideways. Moon is falling sideways. Moon is falling sideways. That means it's kind of like it's not falling directly downwards, right? It's not coming from the top. It's falling sideways. It kind of keeps missing the earth. It keeps missing the earth. It falls, it tries to hit the earth, but it misses the earth and then falls back down. And then tries to hit the earth and then comes back up. And then, it just keeps on falling and falling and falling. And that's exactly what an orbit is, that they're continuously falling. Okay, so that's also Newton's third law example. We'll study about Newton's fourth law, which is the law of gravitation. Like, what is the more, you could say, what determines these forces? That's studied in A2. Like, how do I determine what is the value of this force? That's, Newton's fourth law, which is taught in A2. In fact, that's the first chapter, gravitation. What makes two planets? What determines the force between both of those planets? Okay, I think we went pretty deep. Now, let's move on to a little bit, you could say, let's move on to a few more earthly examples, a few more realistic examples. Newton's third law says that for every action, there's going to be an equal and opposite reaction. Okay. Now that means, for example, if you have, you're wearing Adidas shoes. Now, you know that the force of Adidas is applying to the floor, right? So you could say that this white color force is the force of Adidas on the floor, right? That means there is going to be a force of the floor on your Adidas as well, right? So that means the force is applying an equal opposite force. The floor is applying an equal and opposite force onto you. So what would be the Newton's third law pair for this? It would say that the force of your Adidas on the floor is equal and opposite to the force of floor on Adidas, right? You always have two objects. You cannot talk about Newton's third law pair without saying two objects. This is exactly how questions come. Okay. For example, let's say that you slap a wall. Okay. Now, if you slap a wall, then there is obviously going to be the force on wall due to your hand. But why does your hand hurt so much? Because there is going to be an equal and opposite force by the wall on your hand. So that's why your hand is going to hurt. Okay. Another really good example is that, for example, you have a book on a table. Okay. Now the book it obviously has some amount of force, right? So there is going to be a force due to book, or you could say this is a force on table due to book. Due to book. But why doesn't the book just fall down? Because there is an equal and opposite force on the book. Sorry, force on book due to table. Due to table. Okay, so how would you write Newton's third law? That the force on table due to book is equal and opposite to the force on book due to table. So that's how you would write this Newton's third law pair. For example, another really good example is, did you know that, have you ever, I think, hmm, Araz, do you play sports? Do you play any kind
Yeah,
of sports? Which one?
I play football and basketball.
Football and basketball. Nice. Oh, basketball is pretty fun one. I think, Kaima, did you also play sports or no?
Yeah, I play badminton.
Ah, badminton. Nice, nice, nice. Hania, what about you? Do you play sports? Do you like it or no? I don't.
I'm currently playing badminton, but like before I was playing like basketball and tennis.
Ah, basketball and tennis. Nice. Now, let's take the example of basketball. Oh, ah, Hania, Hania, if you want to jump, okay, what do you do? Like when you try to jump, what do you do? You
Like
try
in
to,
basketball?
exactly. You try, if you want to
Yeah,
jump, what do? You like go up, right? You like try to jump upwards,
yeah,
right?
yeah.
Now, try to imagine it like this. You're not exactly applying a force upwards. You are actually pushing the floor downwards. You can even try doing it. What you're doing is you're not going upwards, you're not jumping upwards. You are actually applying a force onto the floor, because when you like try doing the motion, you notice that I'm actually pushing the floor. And because of pushing the floor, that's why the floor then pushes me up. That's exactly what's happening. So when you try to jump, you are actually pushing the floor very hard, and that's why there's an upwards acceleration on you. Because when you try to jump, so for example, these are your legs. Sorry, I am not in the mood for making very realistic legs at the moment. When you try to jump, what's happening is that, for example, this is your basketball or something. Now, when you try to jump, your legs apply a very strong force onto the ground. And because of that very strong force onto the ground is then going to push you up with an equal and opposite force. And that equal and opposite force makes you go upwards. For example, if you take the basketball, right? Now, why does the basketball bounce back when you hit the basketball onto the ground? This is the basketball. You apply a very strong force onto the basketball, okay? And then that basketball hits the ground. And when it hits the ground, what happens? Doesn't the ball fall back up? Why? Because when a basketball bounces, a basketball bounces, okay? The force on the force on ball, sorry, the force by ball on floor is equal and opposite to what? To the force, to the force on ball due to floor. Did I write that right? The force by ball on floor is equal to force on ball due to floor. Exactly. And that's exactly why a ball bounces back, right? Because you applied a force onto the ground, then the ground is going to apply an equal and opposite force onto the ball. And since the ball is much lighter, that's why it's just going to, it's going to bounce back with such a high acceleration. So that's Newton's third law in so many examples. For example, if you try walking as well, okay, when you try walking, this is your feet, okay. Now, when you're walking, try to notice that what you do is you actually try to push the floor behind, okay. Your feet pushes the ground behind, okay. And what happens as a result? The ground is going to propel you forward. That's also Newton's third law. You're not actually moving forward. When you're running, for example, you are applying a very strong backward force onto the ground, right? And because of the backward force of your feet on the ground propels you forward. The ground is pushing you forward. The ground pushes you forward. And you can imagine that there was no floor and you were floating in space. How would you push yourself to go forward? That's it. Space is an excellent demonstration for Newton's third law. How would you imagine that if you're in space just floating around and you've got no object near you, how will you move forward? Because you've got nothing to push on. So that's why on Earth, you will notice that because you have the ground is going to push you forward. When you were in space, you would have no ground, which means that you will have nothing to push on to move forward. Okay, so Newton's third law is much more deep in so many examples. Okay, now an extremely important example. This is extremely important. This is very common in MCQs. Common in MCQs. Okay. Now I have got three objects over here. So object number one is the earth. Okay. Object number two is the book. Okay. Object number three is the table. Okay. Now, for example, we know that Newton's third law always acts in pairs. So there's always two forces involved and two objects. Okay. Now, for example, if I label one of the forces as the book, okay, the book's weight, to be more precise, this is the weight. Okay. Now, if one of the forces is the weight, what would be the reaction force to the weight? What do you think? Yes, Aras. Any ideas? If one of the forces of the pair is the weight of the book, what would be the reaction force? Would it be like from the table?
Um, would it just be? I think it's from the table. Yeah.
It's on the table. What about you, Hania? What do you think? If one of the forces is the weight of the book, what would be the equal and opposite force? Like, how would we write it?
Wait, would it be from the table and the earth?
Okay, maybe, but not exactly. Yes, Hania, what do you think?
I think from the earth.
From the earth. Oh, okay, interesting. What about you, Kaima? What do you think? If one of the forces is the weight of the book, what would be the equal and opposite force?
No, what with the table?
From the table. Okay. Now, always try to write down. Okay, so the answer is it has nothing to do with the table. Now, how does that make sense? Okay, because we are saying that one of the forces is the weight. What is the weight? How do we define the weight? How do we define the weight? That is the force on book due to what? Is that due to the table? No, it is due to the earth. When we talk about the weight, you have already specified one of the objects, right? Because weight is what? That is the force on the book due to the earth. The earth is pulling the book downwards. Now, what would be the reaction force to W? You always switch the objects, right? So that means that you're literally just going to replace book with earth. That's it. So the reaction force is actually the force on earth due to book. So that means this is going to be the reaction force. Okay, so make sure you remember that. If one of the objects, if one of the forces is weight, okay, make sure you remember that. One object has already been assumed as earth. Okay, because when you talk about weight, that's basically the force on x due to earth. So you've already brought in the earth. You cannot run away from the earth. Okay, now another example. For example, if this is Imran Khan, okay, and this is Imran Khan's weight, okay, and what would be the weight of Imran Khan? As in, how would we define that as Newton's third law of pair? Weight is the force on, it is the force on IK, Imran Khan, due to the earth. Okay. So like this is the force on Imran Khan due to earth. That's exactly what a weight is, right? We know that weight is just the force of earth on us. What would be the reaction force? That would be the force on earth. That would be the force on earth due to Imran Khan. Now, this may turn into a political slogan, which may say, Newton's third law of pair, how would we write that? That the force on Imran Khan due to earth is equal and opposite, equal and opposite to the force on earth, due to Imran Khan. So basically what we're trying to say is that, where did Imran Khan go? Ah, here it is. So that's how you would write down this pair. They're both equal and opposite. So keep in mind that whenever you bring in weight as one of the forces, then you have already taken in the earth. You have already assumed earth as one of the objects. Okay, the other object would be whatever the weight is being applied on. Okay, so a general Newton's third law statement would look like this: that what you're saying is that force on A due to B is equal and opposite to force on B due to A. That's it. So that's a general statement for Newton's third law, that you always have two objects and you just switch the objects. Okay, you cannot have a third object in the Newton's third law pair. Okay, I think I've spoken a lot. I think now it's time for questions. Yes, please take in and absorb this and bring in questions if you have any so far. I'll wait for a minute and two to collect your information.
Wait, so in the book and Earth thing, the reaction force comes from Earth, right?
Which one? This one?
From
Yes, yes,
fir-
yes.
and then force it's coming from the book, but the reaction force is from the Earth. That's what you mean, right?
No, wait, 1 second. The weight is what? The weight is the Earth's pull on the book. Okay.
Yeah.
The reaction force would be the book is pulling the earth with the equal force. Right? The earth is pulling on the book with a force of 500 newtons. Okay. But so is the book pulling the earth with the force of 500 newtons. Does that make sense?
Okay, so the not so the primary force is like the force from the earth or the weight, and then like the
Hmm.
reaction force is the force from the book that's pulling the earth.
Exactly. You could imagine that if the earth is applying a force on the book says, no, you don't. I'm going to apply an equal and opposite force onto onto the object as well.
Okay.
Yes, Hania. Questions?
No,
No?
I don't have any questions till now.
Okay. Kaima, questions so far?
Wait a second, take a look at that. Yes.
This one? Sure. We do lots of questions of these as well. So always think about Newton's third law in terms of action and reaction. In, for example, the book example, the action force was that the earth was pulling the book. What was the reaction force? The book was pulling the earth.
So no questions.
Okay, great. Now, I want you to read these examples by yourself for a minute and two. These are all really, really good examples of Newton's third law. I've said all of these. This is just a summary of what I've said. And do write these down because these are like really, really good understandings of Newton's third law. Because oftentimes, as you know, teachers and schools will just tell you that Newton's third law, action, reaction, equal and opposite, but they don't tell you how to actually use it in practical situations. You see Newton's third law absolutely everywhere. If you're able to understand it conceptually, I guarantee you that every now and then the examiners are going to test Newton's third law so strongly that only the students that have actually learned it realistically will be able to answer the question. You can apply Newton's third law everywhere. That's also why a car moves. Okay, sounds good. Now, question is, this is this is going a bit more into A2, okay, but that's okay. You don't exactly need to learn the answer to this yet, but it's an interesting question. Why does Newton's third law work? Like, what is it in the atoms that causes this? Like, is there, some kind of deep programming into the universe and the laws of physics that there will always be an action and reaction force? But everything is just made out of atoms. Like, do those atoms have some kind of force in them which causes this, equal and opposite reaction force? Why do you think Newton's third law is true? Think about it. It's a very good question. In fact, this question leads us to one of the fundamental forces of the universe. There are only 4 forces that exist in physics. Everything else is just a product of those. The 4 fundamental forces of the universe. The 4, oh, I read 4 two times. 4 fundamental, like every other force is just made out of this. 4 fundamental forces of reality. And no, I'm not going to name the infinity stones, but you could imagine these are the infinity stones of our reality. Number 1 is the force of gravitation. Gravity is one of the most fundamental forces that exists. Okay. And you learn more about this in 8.2 as well. Gravitational force. It's what holds planets together. It's what holds the universe together. It's what holds galaxies together. It's what holds suns and planets together. It's what holds different solar systems and black holes and all of that stuff. That's the force that holds everything in a larger scale together. The second one, which is probably one of the most important one, is the electrical force. The electrical force. And what is the electrical force? That's just the attraction between positive and negative charges. They attract each other. Okay. And what is the other force? That's between like charges, right? So positive will repel, and negative will attract. Sorry, they will both repel. So both of these like charges will repel. That's electrical force. Almost all of the daily forces that you see is the electrical force. And you would say, how does that happen? I don't understand. But I'll tell you the answer in just a second. Number 3 is what we call the strong nuclear force. The strong nuclear force. This is what holds the nucleus together, right? If you zoom into an atom is made of what? It's made of proton, neutrons, and electrons that are orbiting the protons and neutrons, right? But what holds this nuclear together, right? That is the strong nuclear force. That's literally holding your atom together from the inside. Okay. And by the way, the electrical force is also responsible for holding the atom together, because the nucleus is positively charged and the electrons are negatively charged, right? So that means that they will all be attracted towards the center, exactly like the sun and the planets, right? The sun is at the center and the planets are orbiting the sun. That's exactly how the nucleus and the electrons are working as well. Okay. Then you have number 4. This is what we call the weak nuclear force. This weak nuclear force is responsible for nuclear decay. The one that you see in atomic bombs and the one that you see in radioactivity and nuclear power. This is responsible for that. This is slightly more complex and it's not easily understandable, and it's not even like taught in A levels. But these 3 forces are taught in A levels. In fact, you study about all 3 of these forces in more detail in A2. But for an A1, you just like get an overview of all of them without really understanding what they are. Okay. Now, all of these forces are the 4 fundamental forces of reality. Like every other force that you listen, friction, air resistance, reaction force, action force, drag force, upthrust, weight, all of that, they're all a result of these 3. How is that? Now, I'll give you an example of the action and reaction pair. Check this out. What happens is, for example, if you put your hand onto the table, okay? Now, isn't your hand made all out of what? It's made all out of atoms, right? And what is the table made out of? Let's use a different color for it. What is the table made out of, right? It's also made of like millions and millions of atoms. Your hand is also like, if you zoom in, it's made of millions and millions of atoms. Now, all of these have protons, neutrons, and electrons, right? So they've got a plus charge in them that is surrounded by electrons with between them, right? Positive, minuses, plus, and minuses. That's all what atoms are. They're just collections of positive, minus, plus, minus, plus, minus, plus, minus. And isn't that the same with the table as well? In the table, you also have atoms, right? In atom, you have a proton, and then you have electrons surrounding it. Proton, and then electron surrounding it. That's exactly what an atom is. So if you try to push the table, what do you see? If they come too close, shouldn't the positives repel each other, right? And all the negatives also repel each other. So that means whenever two things try to come too close, there is the electrical force that is going to come in contact. The attraction or the repulsion is going to become so strong. And that's why you can't put your hand through the table. That's why when you stand on the ground is pushing you back. Why? Because when your atoms get too close to the atoms of the ground's atoms are going to repel you up. Okay. When you try to push something, the atoms of the whatever object you're trying to push are going to push you in the opposite direction. Okay. Now check this out. So, for example, when your foot is pushing on the floor, you're not exactly touching something. Keep in mind that you don't exactly touch everything in a, you could say, very absolute sense. What's happening is that the atoms of your foot are getting close to the atoms of the floor, right? And then the repulsion between the electrons in both of these creates a strong force that resists compression. And that's exactly what the reaction force is, right? That's what Newton's third law is. Newton's third law was just it was a general expression or a general statement for the layman who knows absolutely nothing about physics. But someone who studies physics, he goes deep and, he realizes, why is Newton's third law true? Why does that, why does that even make sense? That's because of the electrostatic repulsions, that everything is just made out of charges. Okay, so that's how Newton's third law is working. You can use this example absolutely everywhere. You can read it once more and you can let me know if you have any questions, and then we'll move on. Newton's third law, I think it's one of the most beautiful ones because it combines so many of the deep forces that exist. Even friction is a result of the electrostatic force. It's a result of atoms repelling each other. That's it. Hmm. Any questions? Should we move on?
Can I just read it?
Sure. I'll be back in 2 minutes, by the way. Yes, guys. Ladies and gentlemen, should we move on?
Yeah.
Yes, got it?
Yeah.
Interesting. Okay. Yes, Hania, any questions? Does that make sense how Newton's third law works?
Yeah.
Yeah, has anyone ever told you like this?
Like with the atoms and all that.
Yes, Newton's third law. Where does it come from? its practical
Yeah.
uses.
I've heard of the practical uses, but not like exactly like the atoms and all this that we
Ah,
took.
that's exactly how Newton's third law works. Excellent. Okay. Now, okay. And yeah, Kaima, yes. Any questions?
No question.
No. Okay. Okay. Then moving on now, I think we went too deep into the philosophy of Newton's third law. Now let's get back to the actual applications, the mathematics behind it. In fact, from Newton's third law comes another brilliant law. It is the law of conservation of momentum. That is a direct application of Newton's third law of conservation of momentum. Okay, and that's exactly what we're going to do in the next uh 30 to 40 minutes. Okay, so Newton's third law, you guys need a break, or should we continue?
So you can continue.
Okay, yes, Anya, Kaima, what do you think? Should we continue and end a bit early?
Yeah.
Okay, okay, sounds good. So the law of conservation of momentum is basically a direct application of Newton's third law. Okay, now we'll check it out. For example, a rocket. A rocket uses the principle of Newton's third law and the law of conservation of momentum in order to make sure the rocket goes up. What happens is that the rocket, okay, what's happening is basically that the thruster is applying a force outwards, okay, and then the thruster then applies an equal and opposite force onto the rocket, and that's why the rocket is propelled upwards. But it also has something to do with the conservation of momentum. Okay, it'll make sense in a bit, but I'm going to try to explain it. What happens is that, for example, if initially the rocket is stationary, it's not moving at all. Okay, what happens is that because the thruster moves downwards with a downwards momentum, okay, now in order to conserve momentum, the rocket has to move upwards, right? So the total momentum then must be zero, right? So if the momentum before was zero, then the momentum after must also be zero. That means that if the thruster moves downwards with a momentum of 5, then the rocket should move upwards with a momentum of 5 as well. Okay, so what happens is that how does the rocket move upwards? What happens is that we know, I'm going to explain the conservation of momentum in just a bit, that we know that momentum is just what? It's just the combination of mass and speed. Okay. And we know that the total momentum of a system must stay constant. Okay. Constant. Unless some outside force acts on it. Okay. But what about in space? Okay. What about in space? Like, how does a rocket propel itself forward in space? Because in space, there's no air, right? In the balloons example, you remember that the balloon applies force on outside air, okay, outside air or surrounding air, and then the outside air or surrounding air applies force on balloon. That's how a balloon, if you fill up a balloon and then you just let it go, you don't tie it down, what happens is that the air inside the balloon is applying a force towards the outside, right? It's applying a force on the outwards air, and then the outward air is applying a force onto the balloon, and that's why the balloon goes forward. Okay, did you get this example? By the way, I briefly just went over it. Did you get the balloon example which you saw in the video, or should I explain it again? I think I did not do a good job explaining the balloon example. Yes, Anya.
Can you like explain it again?
Ah, the balloon example is slightly complicated. 1 second. Let me show you the video first again. Where was the video? I think it was this one. Ah, check this out. Check this out.
Today we're going to
Balloon
demonstrate.
example.
When I
Here it is.
release my fingers,
So
air
what happens is that we know that the air is coming out, right? But the balloon is going towards the right. Okay, but what's happening? What is the, how would you write the law, Newton's third law from the balloon
pushes
example?
out of the
Check this
balloon.
out.
When I release my fingers, air pushes out of the balloon. That's our action. Our reaction is that the balloon moves with the same force in the opposite direction. If you want to learn more about Newton's third law of motion or ask me a question, check out Scientist Season.
Check this out. So what happens in the balloon is that this is the balloon. And if I can draw a good balloon. Oh, okay, that's not a good balloon, but okay. 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 Now, on this balloon, what happens is that you have air inside, right? You have lots of air inside the balloon, and you have lots of air outside the balloon as well, right? What happens is that this, what happens if you release this? What happens is that this air inside the balloon is going to cause a force outside the balloon. So force inside, no, wait. Force on air outside the balloon is applied by air inside. So basically, you have these air molecules that are applying a force on the outward molecules. Okay, so these particles are getting a force towards this direction. Why? Because of the air inside the balloon. Okay, then because of the force on the outside molecules, the outside molecules are going to apply a force in this direction. Why? Because never mind, I don't think so it's a good example to give. It just makes you even more confused. Let's just I'll give you the balloons example later on. Okay, now let's just jump back to the rockets example. Now, how does the rocket propel itself in space? What's happening is, I'll explain the balloon idea later on when you get the rocket one. What happens is when the rocket is burning fuel, okay, right? That's what's happening in the thruster. The rocket is burning fuel, and then that means the fuel is turning into gas. Okay. Now the gas is shot out of the thruster. Okay. The gas obviously has some momentum. Okay. Now the gas has momentum, and since the momentum of the gas is downwards, okay, in order to conserve momentum, the rocket has to go upwards. That's how the rocket propels itself forward. So the gas, if the gas is going downwards, okay, it has a downwards momentum. But in order to conserve momentum of the total system, the rocket has to go upwards. That's what the conservation of momentum is, that the total momentum must be conserved. Okay. So if the momentum before was what? The momentum before was -5. Okay. And then the momentum upwards has to be +5. Why? Because what was the rocket doing initially? Initially, the rocket was not moving. It was equal to 0, right? It has a total momentum of 0 because nothing is moving. But when the rocket, when the thruster starts, what happens is that the rocket goes upwards and the thruster goes downwards, right? Now, what is the total sum of this? That's just 5 minus 5 equal to 0. Again, the total momentum is still conserved. Okay, so that's how a rocket propels itself forward. I think I should have, kept this example when I taught the law of conservation of momentum. Okay, but that's fine. Okay, what we'll do is I'll first explain it to you in a simpler example, and then the more detailed example should make more sense. Okay, now let's talk about the law of conservation momentum, what that actually was. In fact, actually, I prepared this part for an A2 class, and that's why they already knew the law of conservation momentum, and I was able to better explain that to them. Okay, let's skip that and we'll come to the application later on. Okay, let's talk about what the law of conservation momentum actually is. Okay, It is directly coming from Newton's third law. Okay. What was Newton's third law? Let's use an example to to describe that scenario. You have, for example, two trolleys moving towards each other. Now, this trolley would have a momentum of A. Let's call it PA. Okay. Now, what is PA? That's just, ma times v, right? That's momentums. Momentum is mass times velocity. The mass of the trolley times the velocity of the trolley. Okay. And then let's talk about trolley B. They're moving towards each other. Now, this should have a momentum of PB. Okay. They both have a momentum of PA and momentum of PP. Okay. What happens when they hit each other? When they hit each other, they are going to apply a force that is equal and opposite onto each other, right? Because if both of these hit each other with some amount of momentum, they are both going to get an equal and opposite force on both of them. They're going to collide. That's exactly what happens when two cars crash into each other. So let's draw the forces out. So this would be the force FA, right? Because this, let's do it like this, FA. Okay, so when they collide, so this is going to apply force FA on B, okay? And then obviously B is also going to apply an equal and opposite force onto the trolley A, right? So we know from Newton's third law that FA should equal to FB, right? So far with me, guys? Yes, Ariz? We know that from
Yeah.
Newton's third law, FA is equals to minus FB. Okay. Then we know that if FA is equals to minus, we have to add a minus sign over here. Why? Because they're opposite, right? They're in opposite direction. You have to assume that if FA is positive, then FB should be negative, right? You have to take the vector signs into account as well. Okay. And I know there was another condition of Newton's third law as well, that they must act in same time. Okay, the same time should be applied for both of them. Okay, now let's divide both sides by delta t. That's like the time of collision, delta t. Okay, so what is this? FA over delta t. Have we seen some of that elsewhere? What is force divided by time? Any idea? What is force divided by time?
Uh,
Yes, Anya. What was F divided by delta t? Have we seen that somewhere?
Yeah, it's like the impulse.
Impulse, sure.
Um, I think.
No, that was a trick question. What was change in momentum? That was
change in
F
momentum
into T, right? So
impulse.
can we write that F is equal to delta P over delta T? Would that be right?
Yeah,
Right? So
yeah.
can I replace FA by saying that would be change in momentum of A divided by change in momentum of delta T? And can I write FB as change in momentum of B divided by change in T? Would that be right? Right? Because force is what? That's a change in momentum. Make sense so far? Okay. Now, because they both act at the same time, the time interval for the impact for both of them is the same. For example, they hit each other for just like 0.1 seconds and then they rebounded. What would be delta t? That they would be the same for both of them. So don't they cancel out? Do we see over here that delta PA should equal to negative delta PB, right? Okay. But what does delta PA mean? Keep in mind that change in momentum is what? That's just momentum final minus momentum initial. Okay. That's basically what a change in momentum means. It is the final momentum minus initial momentum. Okay. This is the change in momentum of A. And this is what? This is change in momentum of B. Okay. What is the change in momentum of A? That would just be P final of A minus P initial of A, right? That's the final momentum of A minus initial momentum of A. Okay. Equals to, what would be the change in momentum of B? We are talking about the change in momentum of this trolley. That would just be the final momentum of B minus initial momentum of B, right? But do you notice that it has a negative sign as well? That means that the signs are going to be reversed. If I multiply minus with them, this just comes down as it is. Okay, equal to, I am now going to have to reverse their sign. This becomes what? This becomes PIB minus, no, this is going to be minus PFP. Okay. Now, how about we bring the finals? We bring the finals and the initials on the other side. Let's check. So, how about I bring final momentum of A? Okay. So, how about I bring the initials on one side and the finals on one side? Okay. So, PFA. Okay. So, this stays over here, PFA. And let's bring this on the other side plus PF. We're deriving law of conservation of momentum, by the way. PFP equal to, I'm going to take this on the other side, and this becomes PIA plus PIB. Okay. Now, this is Newton's, this is the law of conservation of momentum. Now, let me define what the hell we've just written. What is this? This is the initial momentum of A. This is the initial momentum of B. Okay. So that means this is basically what? This is PA and PB, their initial momentum. Okay. And what is this? This is the final momentum of A. And what is this? This is the final momentum of B. Now, what does this tell me? This tells me that the momentum before collision, this is momentum before collision, right? This was like before the impact. And this was the momentum after collision. This was the momentum after collision. They should be equal, and this is the law of conservation of momentum. Law of conservation of momentum. And that is how you derive from Newton's third law. That's it. We just like took Newton's third law, Newton's second law, and Newton's third law, right? This was like a combination of Newton's second law and third law. We use Newton's third law that the force must be equal and opposite, right? And then we used the second law where we said that delta P over delta T, right? That's Newton's second law. So this is third law and this is second law, right? We use both of these laws to derive a new law, which is the law of conservation of momentum, which is extremely important. We do lots and lots of questions on that. I haven't gotten to the maths part yet, okay? But this is how you derive law of conservation of momentum from the Newton's second and third law. Okay. Yes. Any questions? You may have a look at it.
Sir,
Yes.
so, well, from what I've learned, like there's elastic and inelastic collisions, right? So
Hmm.
would this will work for both of them, or would it only work for like
Uh,
elastic?
this example is irrespective of whether you're talking about elastic or inelastic collisions. We'll talk about those later in detail as well. What's the difference between them? But this is general throughout the entire universe. The law of conservation of momentum will hold for absolutely every scenario. So elastic and inelastic has to do with kinetic energy than momentum. Elastic is where momentum and kinetic energy both are conserved. Okay. But for inelastic, only momentum is conserved. So kinetic energy is probably lost in, some heat or some sound or something like that. So if this was, for example, a car crash, momentum would still be conserved, although kinetic energy may not be conserved, right? In a real car crash, you see that they both stop. Okay. The momentum was conserved, but that momentum was translated into, bending the car. It was used into bending the car, and then you had a lot of heat energy. The car got pretty hot. You had a very large explosion probably, or you had a very large, you could say, sound. So in elastic collisions, kinetic energy is not conserved, whereas for elastic, kinetic energy and momentum is conserved. But this law of conservation of momentum will hold everywhere. Momentum is conserved everywhere. That's a good question.
Okay, and so is there like any relation between kinetic energy and momentum? Because I
There is, there
remember
is, there
the
is.
test doing, there was a question on calculating the loss of kinetic energy, which I
There
didn't
is,
know.
there is, there is. We will do that. We will do that. Right now,
Okay.
I just stated the law of conservation of momentum. We have all the questions pretty soon. We'll be doing like calculation questions, elastic collisions, inelastic collision, past paper questions, 2D momentum, right? You have momentum at certain angles as well. We'll be doing all of that. Don't worry. But the
Yeah.
foundations of the concept are really, really important before we can get to the questions, because questions for momentum are always pretty tricky. So it always helps to get a great concept. Yes, Hania? Questions, Kaima? Good?
Yeah, also I have a question.
Yes.
For when we're finding like the law of conservation of momentum, can we like just like when the thingy like when there's like an example given, can we just like directly find
Yes,
it
yes,
like
yes. Yes, you don't
after
need
and
to
then
derive it
before?
always. You don't
Okay.
always need to derive it. This is just like a one-time thing. You just need to know that you can come up with the law of conservation momentum just from a very simple example. Okay. But for questions, we'll just need like the last formula, which I'm going to write in just a second. Okay, we don't need to derive it every single time. That's not convenient, and we don't need to do that. Okay, even I haven't opened up this formula yet. This is the law of conservation of momentum, but I haven't opened up this formula yet, which I'm going to do in just a second. Yes, Kaima, any questions?
No, sir.
Okay. Okay, now let's make it much more simpler, and let's get rid of the derivation. The law of conservation of momentum, what is that? We'll just use like two very simple objects, and this is the method that we're going to be using for questions. We know that we have a ball. Let's say you've got two spheres, two objects that are colliding with each other. So m1 has a velocity of u1 and m2 has a velocity of u2. Okay, and let's say that they collide into each other. So let's say that they collide. Okay, then let's say that m1 now has a new velocity v1 and m2 has a new velocity v2. Okay, now we know from the law of conservation of momentum that the momentum before, okay, keep in mind, the total momentum before should equal to the total momentum after collision. Total momentum before should equal to the total momentum after collision. That's an extremely important statement. Now, what would be the total momentum before collision? Wouldn't that just be this momentum plus this momentum, right? So that means m1 multiplied by u1 plus m2 multiplied by u2. That is the total momentum before collision, right? Because they collide at this point and then they, probably move on with different velocities. So the total momentum before collision is just m1 u1 plus m2 u2. Okay. This should equal to the total momentum after collision. What would be the total momentum after collision? That would just be m1 v1 plus m2 v2. That's it. That's the law of conservation of momentum. Total momentum before collision should equal to total momentum after collision. Okay. Extremely important statement. We'll be using this formula like tons and tons of time. Okay. Now, how do we define law of conservation of momentum if there was a 3-mark question? So I'm going to write down the exact definition to you, which will make sure you get all 3 marks. Oftentimes, students will just write this, that the momentum before collision equal to momentum after collision. But for that, you will only get 1 mark. Okay. I'm going to write down the exact definition. You should have this memorized and on your fingertips, because this question gets asked in every single year. Law of conservation of momentum define. How do we define that now? Answer. The total momentum, you should write it word to word. Total momentum before collision is equal to total momentum after collision. For this, you will only get 1 mark. Okay. After collision. In a closed system, okay, without any external forces. This is how you define Newton's third law, law of conservation of momentum with 3 marks. Okay. So the first mark would be that the total momentum before collision equal total momentum after collision. But you also have to write down in a closed system without any external forces. Make sure that you write it down, because this is going to get you the complete mark. If you even miss like a single word out of it, you will not get full marks. Why? Because like absolutely everything is important over it. Even the total word is important, the before word is important, the after word is important, the closed system is important, the external word is important, the force is important. So every single word in this is important. It cannot be distilled down to make it simpler. Okay, written it down. Should we move on? Any questions? Okay.
No.
Okay. Now, question. Let's apply it immediately. This is just, questions from IGCSE. It's pretty simple. We'll be going over the basic IGCSE application, and then we move on to the more difficult ones later. So, for example, if two objects hit each other with a velocity of 5 meters per second, okay, what is their final velocity and in which direction? Okay, so now you have this 1 kilogram ball that is moving towards the right with the velocity 5, and you have a 2 kilogram ball which is moving towards the 1 kg ball with a velocity of 5 meters per second. And then this is, by the way, before collision. And then at some point they collide. And then M1 has a velocity V1 and M2 gets a velocity of 2. Okay. Can you find V1 with direction? Okay. This is just a recall from IGCSE. Find an answer using this formula. Okay. I'll be back in 2 to 3 minutes. Okay, back to the question. I'm sure you missed me a lot. Okay. Yes. Did you get the answer to this question? Ariz, Ania, Kaima.
Yeah.
Yes. What did it come out to?
Um, so -9 ms minus what I got.
Okay. Yes, Hania. What about you?
Towards the left direction.
Okay. Okay. Yes, Ania. What about you?
Yeah, I also got 9 and towards the left.
9 towards the left. Yes, Kaima. Did you get an answer? -9.
Yeah.
Minus
Yeah,
9.
minus. Yes.
-9. Okay, sounds good. If you all got the same answer, then that should be good. Make sure you are aware of the signs. I'm just going to skip the question. So let's say you assume the positive side to be right, then you have to assume that the negative side is left, like, right? And over here, then you have to assume that this is also positive as well. Make sure that you use the formula with these signs. And then, for example, m1 u1 plus m2 u2, right? Now, because this has a negative sign, that means this u value is going to be negative. Okay, so make sure you're aware of the signs. Let's do another question that's similar. For example, if m1 hits m2 with a velocity of 5 meters per second, the mass is 1 kg, and the mass of the other ball is 5 kg. It's not moving at all. Okay, and then we know that after the collision, m2 moves towards the right with a velocity of 2. Okay, and it makes sense because you have a much lighter ball hitting with a great velocity, and it's trying to move a much heavier thing. Obviously, that heavier thing is not going to move pretty fast. It only left with a velocity of 2. But what happened to the velocity of the original ball, m1? Let's check. How do we find out v1? Just use the formula. m1 u1 plus m2 u2 is equals to m1 v1 plus m2 v2. Pretty simple. So 1 kg multiplied by u1 is 5 plus m2 u2 is just 0 because it's not moving. M1 V1, I don't know what that is, but I do know what the mass is. That's just 1 times V1 plus 5 times 2. Okay, I can just substitute the value 5 equal to V1 plus 10. So that means 5 minus 10 is equals to V1, which means minus 15 is equals to V1. Okay, so that means that ball rebounds with a velocity of 15 meters per second towards the left. Why? Because I assigned that the right side is positive and the left side then must be negative. That's how you do this. Okay. Okay, makes sense? Moving on. Another question. Check this one out. M1 is 1 kilogram. It has V1 velocity. So M2 hits it with a velocity of 2. Okay. And the after collision velocity is 5 meters per second. Okay. We know the after collision velocity, that M1 after collision moves away with a speed of 5. And this goes to the right with a velocity of 10 meters per second. Okay. How do you find V1? Again, m1 u1 plus m2 u2 is equals to m1 v1 plus m2 v2. Okay, what is m1 u1? I don't know what that is, but that's just going to be u1 plus. Now, I am assuming that the left sides are negative velocities, right? Vector. It's a vector quantity momentum. What is m2? So that's 5 times negative 2 equal to what is m1? M1 is just the same. 1 kilogram multiplied by negative 5 plus m2 is 2 kilograms. No, it's 5 kilograms. 5 into positive 10. Okay, let's plug in the values. This becomes u minus 10 equal to minus 5 plus 50. Okay, so u is equals to 50 plus 10 minus 5. So u is equals to 60 minus 5, which is 55 meters per second. And that's how you do this question. So 55 meters per second to the left means, sorry, this is going to be towards the right, right? So now I figured out that this is going to be 55 meters per second to the right, because I've assumed that the right sides are positive and the left sides are negative. So that's what the answer was. This is what you wanted to find out, and we have found it out. Okay. Any question? Should I move on?
Yeah.
Okay. Now try this one. Find V1 and V2. Have you got an answer? Yes, Hania.
No, I still haven't gotten an answer.
Okay. Yes, Ariz. Any luck?
I mean, the area where you left at, that's exactly where I am. I can't go further from that.
Hmm. Okay. You gone further?
Yeah,
Or
I'm still thinking. Till now, I'm not
hmm.
able to go.
Okay. Now I'm going to tell you a shortcut. Okay. Now you could do all of this and then you could even solve it even further. But I'm going to tell you a trick. I'm going to tell you a shortcut that you don't need to do all of this. Okay. This is all just a waste of time. It is going to give you the answer. Okay. But it's just going to have to, you're going to have to do like a long derivation to get to the answer. I'm going to tell you a trick. If the masses are the same, if the masses are same, the trick that I want you to remember is velocities are exchanged. That's it. That's just a rule that you should remember. If the masses are the same, you have to spot this. Okay. If you don't spot this, then you won't be able to do this question using the general, the law of conservation of momentum. You will get the answer, but it'll require you to do a very long derivation, which you could have done. But why do we want to do that? Because that derivation is not a part of the syllabus, but you do need to learn that if the masses are the same, the velocities are exchanged, right? So what is the velocity of m1? That's plus 5. Okay, what is the velocity of m2? That's minus 3. That means if they switch their velocities, they should just, exchange them. So that means now m1 is going to have a velocity of minus 3 and m2 is going to have a velocity of plus 5. That's it. That's the answer. So make sure you learn that. Okay. You could get the answer by using the law of conservation of momentum, but you will need to do a long derivation and then substituting values to get the answer. But you don't need to do that. You can just memorize that if m1 is equals to m2, velocities are exchanged. That's a direct result of, you could say, elastic collisions. And we'll learn more about how this is true in elastic collisions. Okay. But for now, you can just memorize that if the masses are the same, the velocities are exchanged. Okay. Pretty helpful fact. And it's in fact, this kind of question often shows up in MCQs. So like MCQs, you don't even need to do the derivation, right? You just, if you remember that the masses are the same, velocities are exchanged. Okay. Now, moving on, last example. Moving on, we are going to deal with sticking objects. Okay. And what do we mean by sticking objects? By sticking objects, we mean that we're going to talk about the momentum, okay, of sticking objects, that objects when they stick together, right? In this case, we see that both objects just, they collide and then they move away. Okay. But oftentimes in collisions, you have collisions where objects stick together, right? For example, in sticking objects, you have an example of either sticking after collision. Okay, an example will make it much more clearer what I mean. And you have sticking before collision. Sticking before collision. We'll do both of these examples in detail. But first, let's do sticking before collision, after collision. Okay, a really good example is, for example, if you have two trains, let's say this train is moving faster and this is moving slightly slower. This train catches up to m2 and then it hits m2. Okay, and it's very likely that when they hit each other, they might then start moving together. They stick together and they start moving with the same velocity. Now, how do we write an expression for this velocity? Because if they're moving at the same velocity, keep in mind that both move at the same velocity. If they stick together, that means that they both move at same velocity. It's an important characteristic. At same velocity. Okay. How to find velocity? Just write down the expression. m1 u1 plus m2 u2 is equal to m1 v1 plus m2 v2. Okay. Now, make sure you note that v2 is equal to v1. Why? Because they're both moving at the same velocity. They're moving together. Okay. Then can't we just say that they move at the same common velocity v? So m1 also moves at capital V and m2 also moves at capital V, right? What if we take v common? Doesn't that become what? That becomes v m1 plus m2, right? And this just comes in as it is, m1 plus m2, and that's it. So if you want to find out v, what do? You just, you find out m1 plus m2 and then divide it on the other side. So v, or capital V, can be found out by using this formula. So what is m1 plus m2? m1 plus m2 bracket, and then, no, sorry, divide it on the other side with this formula. So this is going to be m1 u1 plus m2 u2, right? I just took this and I divided it on the other side. And that's how you'll find their common velocity. You don't need to memorize this formula. You just need to know how to get this formula. How do I derive it? How do I get it? How do I find out the velocity of a common object? Let's do a question. For example, let's say that you've got a car of 1,000 kilograms moving towards a bike at 30 meters per second, and the car is probably, he's texting and driving, and he doesn't see the bike that is literally standing still, and he hits the bike of 100 kilograms, including the person. When the car and the bike collided, they moved together at speed v. How do I find out that speed v? Now I know that after the collision, they both move together. Okay. Like the car is literally going to take the bike with itself. The car is going to take the bike with itself right on top, and they're going to move with the velocity v. What is speed v? m1 u1 plus m2 u2 equal to m1 v1 plus m2 v2. Okay. First of all, let's check what's m1 u1. So that's just 1000 multiplied by 30 plus what is m2 u2? That's just 0, right? Because the bike is stationary. Now we know that v1 is equal to v2. Their velocity is the same after they move together. This is equal to v. So how about I take m1v plus m2v? If I take v common, this becomes what? m1 plus m2. Isn't that just the sum of the masses of the bike and the car? That's what? 1000 plus 100, right? And this was what? 1000 into 30. If I want to find out v, what do? I just divide it on the other side. So 1000 into 30 divide by 1000 plus 100. And that's how you get their common velocity. Let's check it out what that is. 1000 into 30 over 1100. And there you have it. They move together with a speed of 27.2 meters per second. So that's how the car is going to take the bike with itself and then start moving together. Okay. And oftentimes in crashes, you see that you have, objects start moving together. Okay. Okay. I think that'll be all for today. Yes. Any questions so far?
No.
Okay. Yes. Kaima, did you get it?
Yeah, I got it.
Got it. Okay. Yes, Hania, questions?
No, I got it.
Got it. Okay, excellent. Sounds good. Make sure you review these before the next class. Okay, this was all just like pretty basic IGCSE stuff. It was just a recap of the IGCSE rules and how to calculate, momentum using the law of conservation momentum. The derivation is slightly new. You don't do that in IGCSE, and the applications will do them later on as well. But this example will make more sense to you when I talk about sticking objects after collision, sorry, before collision. Okay, it'll make sense then. When you talk about the bullet and the recoil, that'll make more sense then. Okay, sounds good. Make sure you practice this. Make sure you write down your notes. Make sure you write down the definitions, and you can write down the examples as well, and actually understand Newton's third law in absolutely every scenario. That means, if someone asks you a random scenario, you should be able to make an action and reaction pair out of that scenario. Okay. Because in the next class, we'll be doing momentum in 2 dimensions. So what I want you to do is revise forces. Okay. Revise vectors. Make sure you revise that. Revise vector resolution, and revise using Pythagoras, and finding the resultant force of two angle vectors, right? For example, if you had an upward force of 30 and then you had a rightward force of 40, how do we find the resultant force? Revise that, because we'll be using that concept for momentum as well, because we'll be doing questions like this. Check this out. Check this out. We'll be doing questions like this. Previously we were only doing momentum, where the ball goes either left or either right. Okay, but we will get questions very soon that, for example, the ball hit, okay, but they rebounded after collisions at an angle. Okay, those are slightly difficult ones, and you will have to revise your vector resolution to do this question. We'll be doing lots of these questions, right? So for example, imagine this. You see this X ball coming together at B, and Y ball at another angle, right? Like, how do I even write this in the law of conservation of momentum? So we'll be doing all of these questions, but in order to understand this, you should be able to recall the vector resolution part. Okay. Okay. That'll be all for today. I'll send you the recording for this class as well. Okay. You can go through it